Hello, and welcome to the ARC's online TEAS workshop. In this presentation, I'm going to highlight some of the skills you'll need to be successful in the math portion of the TEAS. I'm going to be covering a lot of ground in a short time, so feel free to pause and rewind if you need to. I'll first talk about the structure of the math section of the TEAS. Then I'll go over some strategies for math standardized tests. The rest of the time, and the largest part of this presentation, will be spent mentioning many of the topics that you might be asked about on the math section. So first, what can you expect when you sit down to take the math portion of the TEAS? First, notice that it's worth only about a quarter of your total score on the test. So while the math section is important, it's not the most important. So make sure that you give adequate time to study the other sections of the test. And on this part of the TEAS, you're going to be given 54 minutes to complete 36 questions. That works out to 1.5 minutes per question. So make sure that you pace yourself. If you find yourself spending more than, say, 2 minutes on a question, make your best guess and move on. You don't want to run out of time on a difficult problem, while there might have been 3 or 4 easier problems that you could have answered in the same amount of time. So first tip about word problems. So in the math section of the TEAS, you're going to encounter a lot of word problems. So finding a strategy that works for you is essential to working efficiently. One possible way to tackle a word problem is to first quickly skim through the problem, looking for keywords that might help you decide what type of problem it is. Start thinking of formulas and techniques that you can use on such a question. Next, read through the question again more slowly. Focus on the quantities and information that you're given and what you are asked to find. Think about where these might fit into the formulas and techniques you thought of earlier. Now start fitting all the pieces together and working toward the solution step by step. The most important thing that you can do, however, is practice, though it's kind of a cliche. It's much easier to recognize and answer a question that you have seen similar questions before than to apply these problem-solving techniques in the moment. You'll most likely need them as a fallback, but your first line of defense should be your prior experience. Next, a note on estimation. Because the test is multiple choice, you often don't need exact numbers in order to answer a problem. For instance, here we have a problem that says, if Maria left a $10.16 tip on a breakfast that cost $86.89, approximately what percentage was the tip? So to calculate the percentage, we need to divide the tip amount by the amount that Maria spent on her breakfast. But we don't actually need to be exact. So we can approximate her $10.16 tip as that's about $10, and $86.89, that's about $90. So using these numbers, we can divide them to find that the tip percentage is about 11%. The option that's nearest to that from the options that were given is A, and that turns out to be the correct answer. So using some estimation techniques can save you a lot of time typing in a lot of numbers into your calculator or doing some mental math. Now on to the topics that you'll need to be familiar with on the TEAS test. So first, decimals. You'll have to be very familiar and comfortable with place value and reading decimal numbers. The decimal point is always just to the right of the ones or units place and separates the whole part of the number from the fractional part. The value of each place increases as you go to the left and decreases as you move toward the right. Each place value is 10 times the place immediately to its right. And a digit in the tens place, for instance, counts for 10 times as much as the same digit in the ones place. So make sure that you know how to add or subtract two decimal numbers by lining up their decimal points. Also, remember that because our decimal notation is based on the number 10, you can quickly multiply a number by 10, 100, 1,000, etc. by shifting the decimal point to the right, and which will make the number bigger. Likewise, you can divide quickly by any power of 10 by moving the decimal point to the left, making the number smaller. That can also save you a lot of time. You'll also need to be familiar with fraction notation, how to add, subtract, multiply, and divide fractions. Know how to do these with mixed numbers and improper fractions as well. Also, if the numerator and denominator of a fraction have a common factor, you'll often need to divide both the top and bottom by this common factor to reduce the fraction to lowest terms. There may be several questions that require you to convert between various kinds of numbers. So to convert from a fraction to a decimal, you'll divide the numerator by the denominator of the fraction using either your head or a calculator, and that will convert it to a decimal. Converting back is only a little bit trickier. So to convert from a decimal to a fraction, you'll look at the last digit in the decimal and look at its place value. So in this case, the last digit is this 5 here, and its place value, well, it's in the hundredths place. So we take the digits of the decimal number and then we put the place value in the denominator, and that becomes our fraction. In this case, both 75 and 100 have a common factor of 25, so we reduce it. We reduce the fraction to lowest terms. It turns out to be 3/4. Also, make sure that you understand percent notation. The word cent is Latin for 100, so that's a great way to think about, or a great way to remember what percents mean. So think about like how many years there are in a century. There are 100 years. Or how many cents make a dollar. 100 cents make a dollar. So a percent is just a fraction with an unwritten denominator of 100. You might see a question similar to this on the test, asking what percent is 24 out of 200. For something like this, you'll place the is number over the of number, and then you can divide those to get a decimal, and then you can convert those to, or convert that decimal to a percent. So in the same vein as what we just talked about, how do you convert between decimals and percents? This is very easy. You can convert from a decimal to a percent just by multiplying that decimal by 100. And so remember the trick of moving the decimal point. So you can move it 2 places to the right. To convert from a percent back to a decimal, you just do the opposite. Move the decimal point to the left 2 places. There might also be some questions about converting to or from Roman numerals. In a Roman numeral, every letter has a value. So the letter M is worth 1,000, letter D 500, and so on. So the only tricky part of Roman numerals is that if you have a larger letter, a letter that's worth more, followed immediately by a smaller number, then you add their 2 values together. But if they're in the opposite order, a smaller number is followed by a larger number, then you subtract. So for instance, here we have MC. M is 1,000, C represents 100, and because we have larger followed by smaller, their values add, and we get a 1,100. If we flip their order, we subtract instead. And so the value of this is now 900. So if you have many Roman numerals, or if you have a Roman numeral that's made of multiple letters, then you split it into pieces. Here we split it into the thousands, hundreds, and the units. So if we compute each one of these individually, it turns out that this Roman numeral is equal to 1,906. Also make sure that you're very comfortable using the correct order of operations, which is parentheses, exponents, multiplication or division, and addition and subtraction. If 2 operations that are next to one another have the same, are in the same category or have the same precedence, we say, then apply them left to right. So for instance, in this problem on our right, we first look at this sub-expression inside the parentheses. We see an exponent, so we first raise 2 to the 4th power, and that gives us 16. Next, we're still working inside the parentheses. We see division, so we divide 16 by 2, and that gives us 8. The sub-expression inside the parentheses has now been reduced to a single number, so we remove the parentheses. Now we see 2 operations, subtraction and division. Division comes first, so we do 8 divided by 8, which is 1, and then we do 2 minus 1, which is 1. So that is our final answer using the correct order of operations. Now on to algebra. You'll have to know how to solve equations with one variable. So for instance, to solve this equation on the right for x, we want to isolate the variable x on one side of the equation and all the numbers on the other side. So it can sometimes be helpful to work in sort of reverse PEMDAS order. So notice that we start by moving all the terms with x in them to one side and all the numbers to the other side. To get rid of this 3x on this side and move it to the other side, we subtract 3x from both sides. That will give us 0 on this side. And likewise, to move the negative 10 to the other side of the equation, we add 10 to both sides, which gives us 0 here. And so we do that addition, and this is our result. So you see that we did our addition and subtraction first. Now that we're done with that, now we do our multiplication and division. Since there's a 2 stuck to this x, we divide both sides of the equation by 2 and get our final answer, that x is equal to 11. And if you have a little bit of extra time on the test, you will definitely want to plug this answer back in to the original equation to make sure that you got it correct. Next, the FOIL method. FOIL stands for first, outer, inner, last, and it's a mnemonic to help you remember how to multiply together two binomials. We first multiply the first two terms together, and then the outer two terms, and so on. And then we add up every single one of these results. Now, how to solve inequalities such as less than, greater than, they're equal or equal to cousins, and not equals. Solving this is pretty easy. You apply all the same techniques that you used for regular equations. The only difference is that if you're multiplying or dividing by a negative number, then you have to flip the alligator mouth or this inequality symbol. So you see that we got to this point in our equation, and in order to isolate the variable y, we needed to divide by -8, and when we divided by -8, the inequality symbol swapped its direction. But that's really the only difference between inequalities and equalities. You also need to know how to solve equations with absolute values in them. The absolute value signs take whatever's in between them and makes it positive. So if you take the absolute value of, say, +3, well, the +3 is already positive, so it just gives you back 3. If you take the absolute value of -3, well, it switches it to a +3. So it takes anything inside it and makes it positive. So once again, solving these type of equations uses all the same techniques that you used previously to solve normal equations, but with a couple curveballs. So to solve an equation like this that we have on the right, we start by treating everything inside these absolute value bars as one unit, one chunk. And we solve for that as if we're solving for a variable. So first we'd move the 3 to the other side and then divide both sides by 2. And here we have it isolated. So that's the first step. The next step is that we split this into two equations. One gets a positive sign on the right side, and the other gets a negative sign. So we took this 8 and made it positive in one equation and negative in the other. Now you just solve these two equations normally, and you get two results. So x can be either of two values. It can be either -2 or 14. Once again, it's a great idea to plug these back into the original equation to make sure that they're correct. Next, make sure that you know how to use the rate equation and are able to recognize problems for where it is needed. So, for instance, this problem here, we're given the distance that a car travels and how long it took to travel. So we can use the first form of the rate equation, plug in the 360 for the distance and 5 hours for the time. If we divide those, it turns out that gives us 72 kilometers per hour. Then, now that we know that, we're not quite done with the problem. They ask us how far will the car travel in 9 hours. Now we can Now that we know the rate at which the car is moving, we can plug the 72 that we just found earlier and multiply that by the 9 hours, and it turns out that that gives us 648 kilometers. So the answer is D. Next, I'm not going to read all of these formulas, but you'll need some measurement skills. You'll need to understand perimeter, area, and volume, and know some formulas for some basic shapes. So perimeter is the distance that you'd have to walk if you were to walk all the way around a 2D shape, and its units are length, so feet, meters, inches, something like that. Area is the space enclosed by a 2D shape, and its units are length squared, so feet squared, meters squared. And then volume is just the 3D equivalent of area. It's the space enclosed by a solid or a 3D shape, and its units are length cubed. So if you're ever working a problem and you realize that your units are wrong for whatever quantity you're trying to compute, suppose you're trying to compute volume and you end up getting a unit of meters, well then you might want to go back and check through your work. You might have made a mistake somewhere. The last thing I'll say is that this Greek letter pi, it really represents a decimal number with an infinite number of digits, but once again we can use estimation techniques. We don't have to type all those into the calculator. 3.14 will get you close enough most of the time. And if you're working with fractions, then 22/7 is also a good approximation. So many problems will ask you to convert between different units for measuring the same thing. For instance, the weight of maybe a young child could be measured in pounds or grams or kilograms. So to change from one unit to another, you'll need a conversion factor, which is just a fraction that tells you sort of what the exchange rate is between two quantities. So to solve a unit conversion problem, first start by writing the quantity that you started from, or that you're given, as a fraction with a denominator of 1. Then write the conversion factor, or factors, with the desired unit on the top and the unit you are converting from on the bottom. Then multiply all the fractions together. It might be necessary to string together multiple conversion factors to get the result you want. For instance, here we didn't go directly from grams to pounds. We went first from grams to kilograms, and then from kilograms to pounds. So we used 2 conversion factors. That got us our final result. Here on the right, I have a couple common conversion factors listed. Of course, there are many more, so be sure to study some of these and remember them. Next, make sure that you're familiar with the common metric prefixes. So a metric prefix modifies its base SI unit, such as meters or grams or liters. It modifies it almost like a place value. For instance, a kilometer, kilometer, is 1,000 meters, and 1 milliliter is 1,000th of a liter. So you might like to use this mnemonic to remember the most common ones, or you're welcome to make up your own. The sillier the better you remember it. So once again, remember our trick of moving the decimal point, because notice that each one of these prefixes multiplies or divides by a power of 10. So you don't actually need to do any math or calculator magic to make this work. You can just move decimals, or move decimal points. There might also be some questions about converting between Celsius and Fahrenheit temperatures. These are the formulas you'll need to memorize. Notice also that a Celsius degree is a bigger change in temperature than a Fahrenheit degree. It takes only 100 Celsius degrees to go from freezing to boiling, but it takes 180 Fahrenheit degrees. So a Celsius degree is almost twice as big as a Fahrenheit degree. And that can help you remember which formula goes with which temperature measurement. So now on to the last section, which is data visualization. So you'll be asked to either interpret graphs or decide what kind of graph to use for a certain data set. So there are a couple kinds of graphs that I'll go over, but they all have the common feature that usually the horizontal axis, if it's there, measures the independent variable. That's the variable that you manipulate or that you're studying the effect of. And the vertical y-axis measures the dependent variable. That's the variable that you're trying to determine the effect on. So first, the humble bar graph. It's very simple. It is used to display categorical data, and it usually shows the number of items in each category. For instance, in this graph, we have 4 categories, and they're in no particular order because they're just categories. We could have put walnuts first, and it wouldn't make a difference for what we're trying to show. So with a bar graph, we can easily compare the sizes of the different categories. We can see at a glance that peanuts are the most popular and walnuts are the least popular. And it's much easier to do this with a picture than reading some list of numbers. So that's why we use graphs. Next, pie graphs. These are also used to display categorical data, but pie graphs are usually used when the total is meaningful, so when all the data adds up to something. And so often that something is 100%. So each category is given a slice of pie, and the larger the slice of pie, the larger contribution that category has toward the total. Scatterplots are also a widely used graph type that shows numerical data. Often, scatterplots are used to show the relationship between 2 quantities. The position of each point in a scatterplot is determined by the value of the independent and dependent variables at that point. If there seems to be a connection between the independent and dependent variables, we call the variables correlated. And a connection between 2 variables will show up as a clearly recognizable shape or curve. So for these 2 variables here, we can see that they very clearly follow some sort of line. So in this particular graph, each point represents a business day. It appears as though as the temperature increases, then the amount of sales that the ice cream shop gets in that day also increases. So because there seems to be a connection between these two, we would say that these 2 variables are correlated. However, remember that just because 2 variables are correlated doesn't mean that one causes another. So suppose that I plotted the times when my watch chimes versus the times when a clock tower chimes. These events would be perfectly correlated. Every hour, both my watch and the clock tower will chime at almost the same time. But neither of them cause one another. They're both independent of each other, and it turns out that both are caused by the passage of time, right? And the last graph is the line graph. So it's also used for numerical data. It's a little bit different from a scatterplot in that instead of just having a bunch of separate points, we now connect these points with lines. And in scatterplots, the horizontal axis could really measure anything, and the same is true for line graphs. But most often line graphs are used to show the evolution of some quantity over time. So in this particular plot that I have here, we're showing the population numbers of various species over time. So you can tell at a glance whether a species is thriving or declining based on the direction its curve seems to be going. So that wraps up this ARC presentation. I hope you found it useful. Thank you once again for using the ARC's resources, and I wish you the best of luck in all your studies and on the TEAS.